Swayam Prabha. Digital India. Educated India.
Yeah, please focus and please take a notebook and write. So you see, we are trying to understand rigid motions, okay? And what I have been saying is that the way to approach rigid motions is to realize that rigid motions are just, up to a translation, they are orthogonal isometries, which, have determinant 1, plus 1, okay? And I've already shown you, we have already seen that if you take, if you take if you take a member of the orthogonal group of order n, okay, so these are n by n orthogonal matrices, and they are defined by this condition: the transpose AA is equal to the n by n identity matrix, okay. Then by taking determinants, you can show that the determinant is plus or minus 1, okay. And we say that if the determinant is plus 1, then it is orientation preserving, and if the determinant is minus 1, then it is orientation reversal, okay. Now, so the important thing is that rigid motions are nothing but, compositions of an orthogonal isometry which preserves orientation followed by a translation, okay. And that gives a linear algebra interpretation of rigid motions, and this is required to show that if you take a curve and move it by a rigid motion, its its curvature and torsion do not change, okay. So let me make the following statement. Again, I would like you to see a little bit about the orthogonal matrices, okay. I want you to also realize that orthogonal matrices also represent ordered orthonormal bases, okay. So this is again another important interpretation, okay. So let me explain that. So you see, so you start with orthogonal matrix A in ONR, okay. So it's a real orthogonal matrix. So you have this condition that transpose AA is identity n by n. So this identity n by n is the n by n identity matrix, which has only non-zero entries on the diagonal, which are 1, all other entries are 0, okay. It's the identity matrix of size n, all right. And see, if you look at it carefully, then you see, if you write, so what is A? See, if you write A as, column vectors, okay. So A is, suppose you write A as Aij, okay. Then A is just A11, etc. up to A1n, then A21, etc. up to A2n, and so on. If the ith column will be I1, etc. to AIN, and so on. It goes on up to AN1, etc. to ANN, okay. And you see, if you call this column as the ith column, then this is CIA, right? So A is just, simply C1A, C2A, dot 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 CNA. These, you are just seeing A as, n columns, okay. And what is the importance of this kind of representation? This A also defines a linear transformation, and that linear transformation is precisely given by the linear map that sends the ordered standard basis to these columns. So A defines LA from Rn to Rn. This is a linear isomorphism such that EI, the standard basis vector, goes to, so I should write EI maps to EI maps to LA of EI is nothing but, the column IA, where the column IA is thought of as a column vector. Okay, and notice that column IA is, if you write it in EI notation, column IA is sigma, Aij Ej, j equal to 1 to n, right? And so this is how you write it as a linear combination of components, all right? And this is how you write it as a column vector, right? Now anyway, see, if look at this statement here, what is happening is that if you write it as columns, basically what you're saying is transpose, so let me just put a smaller bracket, transpose column 1a, column 2a, dot dot dot, column na, times column 1a, column 2a, dot dot dot, column na is equal to the identity matrix. Okay, and you see, if you write it like this, what will you get from this? See, the transpose of this, okay, is the see, if you transpose a column, get a row, okay, and then you get the matrix whose rows are the transposes of these columns. Okay, so basically what you will get is this part will become transpose column 1a, okay, that is a row now, then transpose column 2a, and so on, transpose column na, okay, times on the right side I have c1a, c2a, dot dot dot, cna is equal to the n by n identity matrix. Okay, but what does this actually tell you? What this tells you is the following thing. See, it tells you the following thing. It says transpose CIA into CJA is delta ij. That's what it says. Okay, because transpose CIA CJA is the ij entry of this product, and the ij entry of this product, which is the same as the ij entry of the identity matrix, is delta ij. The delta ij is the Kronecker delta. But what does this tell you? See, this is, if you see this as vectors, this is actually the dot product of CIA and CJA. So this is the CIA column vector dot CJA column vector is equal to delta ij. Okay, and what does this tell you? This tells you that all the columns are there are two things you are able to see from this. All the columns are mutually orthogonal. The dot products are 0 when you take different columns. Also, they are length 1, because if you put I equal to j, okay, a vector dot itself is its modulus squared, and that is 1, and the modulus is positive, so the modulus must be 1. So what this gives you the following thing. It tells you that C1a, etc., CNA, they form what is called an orthonormal set. Okay, so C1a dot 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 CNA form an orthonormal set of vectors. Okay, and orthonormal means they are orthogonal, dot products are 0, and normal means they have unit length. So orthonormal should be interpreted as a mixture of two things: orthogonal, which is perpendicular, the dot product is 0, plus unit length. This normal is that the length is normalized to 1. Okay, so it's unit length. So it's a set of n mutually perpendicular vectors which have length 1. Okay, now the beautiful thing is that any set of orthogonal vectors, mutually orthogonal vectors, is always linearly independent. Okay, so this being a maximal set of, so if you take a set of n mutually orthogonal vectors, then this will be a set of n linearly independent vectors, and that is a maximum possible because the dimension of the space is n. See, this is a result in linear algebra, that when you take a vector space of dimension n, okay, it will have, a basis of n elements, okay, and any other basis, any two bases will have the same number of elements, and it will be this n, okay, and this n will be the max, and this basis property will make it that the basis elements are not only linearly independent, it will also make that they span. That means that every element can be written as a unique linear combination in terms of these basis elements. The uniqueness of the coefficients is ensured, okay. But if you look at it only from the point of view of linear independence, then for a vector space of dimension n, the any maximal linearly independent set will contain only n vectors, okay, and that will automatically span, okay. So a maximal linearly independent set will always be a basis. Similarly, if you look at it in terms of spanning sets, okay, a minimal spanning set will have the same cardinality as the dimension of the vector space. So in this case, a minimal set of vectors that will span the whole space, that means that will allow every other vector to be written as linear combinations of these, okay, that minimal number is also n. So that means if you take less than n vectors, okay, then you cannot span the space, and if you take more than n vectors, it will not be linearly independent. That's the whole point, okay. So these orthogonal vectors are going to be linearly independent, and this unit length is an extra condition, okay, that is coming. Now, because of this, what happens is that I want to say, therefore, that such an orthonormal set of vectors, okay, is always a basis, okay. So, let me say one more thing. When I write this C1a, etc., CNA, you see the order is very, very important, okay. So, I will just put a square bracket like this, okay, so that actually it's, if you want, it is actually the matrix with the rows, with the columns already ordered, first column, second column, and so on, okay. And so I will just say they form an ordered, so this ordered is very, very important. It's an ordered orthonormal set of vectors. And the point is, actually what I'm trying to say is that this orthonormal set of vectors, because there are n of them, because of orthonormality you have orthogonality, because of orthogonality you have linear independence. So you have n linearly independent vectors, therefore they must be a basis, okay. Therefore this is not only an ordered orthonormal set of vectors, it is actually an ordered orthonormal basis. And then the claim is, there is a bijection between all the orthogonal matrices and the set of all ordered orthonormal bases of Rn, okay. That is the interpretation, okay. And if you take any such orthogonal transformation, what is the if you take it as a matrix and think of it as a transformation, what is the transformation doing? The columns of the orthogonal matrix are the orthonormal basis elements, and what this linear transformation is doing is simply mapping the standard basis in order to the the ordered orthonormal basis, okay. And notice that these orthogonal transformations, they are the linear isometries, and linear isometries preserve the dot product, okay. Therefore they preserve dot products. So what will this do? You see, these transformations will, if two vectors are perpendicular, you apply this transformation, the images will also be perpendicular because it preserves the dot product. So if you start with any orthonormal basis, okay, if you start with any set of mutually perpendicular vectors and apply this transformation, the images will automatically become, mutually perpendicular. And that's exactly what is happening. You see, E1, E2, etc., En, they are mutually orthonormal vectors. I mean, they are an orthonormal basis. They are mutually perpendicular, length 1. And what this matrix is doing is, when you apply it, it's taking E1 to the first column vector, E2 to the second column vector. So it's taking this ordered basis E1, E2, etc., En to the ordered orthonormal basis given by C1a, C2a, etc., Cna, okay. And it will not do it only for for this standard ordered orthonormal basis, it will do it for any orthonormal basis, The point is it will take perpendicular vectors to perpendicular vectors. That is the reason why it's called an orthogonal transformation. Okay, that is the geometric reason for that word. Okay, it maps perpendicular vectors to perpendicular vectors. Okay, so let me say the following thing. The set, C1a blah 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 CNA forms a basis for Rn as a vector space over R. And why is this? This is because for this is something that's very easy to verify, and you already know this for ijk. If you take ijk to be the standard unit vectors, along x, y, and z directions for 3 space, it is the same verification. So the first thing is, why is it linearly independent? Linear independence. If you take a linear combination of this and equate to 0, then every coefficient must be 0. That is linear independence. If there is a linear combination of this that is 0 with some coefficient not 0, it means that gives you a linear dependence relation. And linear independence is the point, is the property that there is no linear relationship between these things. There is no linear dependence relation between these things. And a linear dependence relation is just a linear combination of these things equal to 0. So if you have to take a linear combination of these things, equate to 0 and show that every coefficient you have multiplied, all the coefficients are 0. But that comes just because of the orthogonality. So you see, so let me write this. Suppose, sigma I equal to 1 to n, lambda I CIA is 0, okay, where lambda I are real numbers, okay. To show linear independence, you have to show every lambda I is 0. All you have to do is just, if you want, multiply, dot it with CJA, dot with, CJA. This will give you summation lambda I equal to 1 to n, CIA dot CJA, okay. And when I write here, there's a little bit of abuse of notation. I am seeing this as dot product of vectors, and I am seeing the vectors as column vectors. So the way to write this as vectors is I put dot. If I want to write as matrices, I should write TCIA CJA. I would write it like this, okay. And this is just matrix multiplication, okay. So this is 0, okay. But then you see this will survive only for I equal to j. Otherwise, you will get delta ij. So you will get, summation lambda I delta ij is 0, I equal to 1 to n. And then you see this will only survive for j. So what you will get is you will get lambda j is 0. Okay. And this is true for all j. So that's linear independence for you. If there is a linear relationship, if a linear combinations of these CIAs is 0, then every coefficient must be 0. You cannot have a linear combination of these guys equal to 0 with some, even not with even at least one of them, one of the coefficients non-zero. Because if such a relation exists, it's a linear dependence relation. There should be no such dependence relation. That's what linear independence is all about, okay. That's the first thing. Then the second thing is that this also spans. That is, every vector can be expressed as linear combination of these vectors. So spanning property, that is very easy to write down. That's because let V belong to Rn, and you write and try V is equal to sigma lambda I CIA, okay, I equal to 1 to n. All right. Now, how do you find the lambda I? Again, you simply dot with CJA. So you dot with, of course, dot with means take inner product, standard inner product with CJA. What you will get is you will get V dot CJA is equal to, here on the right side I'll get summation I equal to 1 to n lambda I CJ A dot CIA. By the way, I can write it as A dot CJA or CJA dot CIA because dot product is symmetric. Then the other thing is dot product of a sum of vectors is sum of the dot products. Dot product distributes over addition, okay. And scalar dot product of one vector with the scalar times another vector, I can pull the scalar out. Okay, so we say the dot product is bilinear. It's linear in each of the arguments. Okay, so I can do all this, and finally the point is that this is delta ij, and therefore this is just going to give me lambda j. Therefore, you get if you start with v, if you start with a v, write it as lambda I cia with lambda I unknown. Okay, try to express v as linear combination of its cia's. Then you can find the lambdas. The lambdas are just the dot product with the corresponding column. Okay, therefore lambda j exists and equals v dot cja. Okay, of course I should have put, for v I should have put a arrow on top. I am not doing that. It's understood that this is these are vectors. Okay, so therefore the moral of the story is that if you take an orthogonal matrix, all the columns in order, they form an ordered orthonormal basis. And conversely, you take any ordered orthonormal basis and simply write it as a matrix. That matrix is orthogonal. That's all. Okay, so you have this very beautiful description. So set of orthogonal matrices. This is ON. Okay, in fact it's not just a set. In fact, actually this is actually a group under matrix multiplication. Okay, but I am writing it as a set because I am going to compare it with another set, and the other set a priori doesn't seem to have any multiplication structure. Okay, so this is in bijection with ordered orthonormal basis of Rn, and the bijection is very simple. You start with an A, which you write as column 1A dot column NA. You just send it to these columns, column 1A dot column NA. Okay, and of course here the square brackets are you think it's just to think of it as an ordered set. Okay, or maybe it's even good to put round brackets if you want. Really doesn't matter. But on the left side these are matrices. On the right side you are only worried about the columns in the given order. Okay, and this is a bijection. Okay, so this is one fact. Then there's another important thing that what do these orthogonal matrices do? The linear transformations defined by orthogonal matrices are going to transform orthogonal vectors to orthogonal vectors. Okay, so you see something's troubling you. No, I am saying that if you want to, so the idea, what is the spanning idea? The spanning idea is that you have to show that every vector can be written as a linear combination of these column vectors. So I am saying that if you assume that you can write it as a linear combination of these column vectors with these lambda i's as a quotient of the ith column vector, then you can actually determine what the lambda I is. And the lambda I is given by just dot of v with the ith column vector. Ith column vector is known, v is known, so the dot product is known, so therefore the lambda I is known. Okay, therefore you can write certainly v as the linear combination of these column vectors, and you can do this for any v, and that shows that these column vectors, their linear combinations cover the whole space. It is another matter that these coefficients lambda I are unique. That is what the earlier one, namely the linear independence, says that those coefficients are actually unique. Okay, so the existence of the coefficients is the spanning property. The uniqueness of the coefficients is the linear independence. Okay, so that's all I'm saying, right? So here is another remark. What an orthogonal the reason why an orthogonal matrix is called an orthogonal matrix, because the linear transformation defined by that matrix preserves orthogonality. It's as simple as that. Okay, the reason why an orthogonal matrix is called an orthogonal matrix. Is, well, in fact, there are two reasons. One is the columns of the matrix are orthonormal. And if you take the transpose, you see the rows are also orthonormal. Okay. Because the transpose of an orthonormal matrix, orthogonal matrix is also an orthogonal matrix. Okay. Therefore, after all, the transpose of an orthogonal matrix is actually its inverse. And the inverse of an orthogonal matrix is actually orthogonal. Okay. So, if you see an orthogonal matrix, you see that all the rows are orthonormal, all the columns are orthonormal. Okay. That is one thing. The other thing is that the linear transformation that it defines, it's a linear isometry, it preserves the dot product, so it preserves orthogonality. Okay. Its rows are orthonormal. Number 2, its columns are orthonormal. Number 3, the linear transformation it defines preserves the orthogonality. Since it preserves dot products. Okay. So when I say the reason, it's any of the following. It's any of the following. Okay. And as a nice application of this, if you give me two ordered orthonormal set of vectors, you can very easily find a linear transformation that takes this to that. Okay. So here is a cute application of this. Suppose I have, suppose I call V1, suppose V1 etc. Vn is an ordered orthonormal set, ordered orthonormal basis. Okay. And suppose W1 etc. up to Wn, is another ordered orthonormal basis. Okay. Then there is a linear transformation which takes this ordered orthonormal basis to that. And that's very, very easy to find, because you see, you take the standard basis E1 etc. up to En. Okay. What is the orthonormal transform? What is the transformation that takes E1 En to V1 etc. Vn? It's precisely this matrix V1 etc. Vn. This is your matrix A. You take all these ordered orthonormal bases and simply treat them as column vectors and form that n by n matrix. That's an orthogonal matrix. Okay. And the linear transformation defined by that matrix will take the standard basis to these in order. Similarly, you have one more fellow here. You take B to be simply the this matrix W1 etc. up to Wn. Okay. Then this is again an orthogonal matrix, and there is this LB that takes E1, E2 etc. En to this. Now you see this LA and LB are linear isomorphisms. Okay, so you can go. So if you want to go, so this diagram commits. So what I want to say is that this L is you start from here, you first go here, and the way to go from here to here is apply LA inverse. And then apply LB, then go from here to here. So L is nothing but first apply LA inverse, then apply LB. And what is that? LA inverse, the matrix of LA inverse is just A inverse. Okay, and the matrix of LB is just B. So as a matrix, it is just BA inverse. Yeah, so no. The point is that when you write LA, you are operating on the right. It's right multiplication. Okay. So therefore, you see, if I give you an orthonormal basis and give you another orthonormal basis, how do you find the linear map, which the matrix of the linear map that carries this to that? All you have to do is that you have to compute this B A inverse, and the A and B are just those column vectors put together to form the corresponding orthogonal matrices. Okay. So by the way, so this is in ON. So I think I have to update this, and this guy is also in ON. And notice that this is also this BA inverse is also in ONR. They are all orthogonal transformations. Okay, so it's a very easy way to write down how to take one orthogonal matrix, orthogonal set of orthonormal set of vectors and map it to another orthonormal set. Okay, and of course you can ask this question that do orthonormal sets exist? Okay, one answer is standard basis is orthonormal, and then you take any orthogonal matrix, it's going to give you an orthonormal basis. But then what is the connection with any arbitrary basis? So this is something that you come across when you do a course in linear algebra. You start with an arbitrary basis, you can modify that basis to get an orthonormal basis, and this is the so-called Gram-Schmidt orthonormalization process. Starting with any basis, you can modify that basis and arrive at a new basis which consists of orthonormal vectors. Okay, so this is a very standard thing in in linear algebra. Okay, and fine. So now, having done all this, we come to the following statement that I want to come to the following statement, namely, what is the significance of the determinant of the matrix? So the significance of the determinant is that the determinant of an orthogonal matrix can only be plus or minus 1, because determinant squared is 1 comes from transpose A is equal to identity by applying determinant on both sides. Okay, so determinant squared A is 1, therefore determinant A is plus or minus 1. What is this? When is determinant A plus 1? When is determinant A minus 1? So the truth is that what does the orthogonal matrix do? It takes an orthonormal basis and it changes it to another orthonormal basis. Okay, now what will happen is that if it changes the order in the cyclic order in which all the basis elements are written, okay, if it does that, then there will be determinant minus 1. If it does not change the cyclic order, okay, then the determinant will be plus 1. Okay, and so if you want to see it, the easiest way to see it is look at n equal to 3. Okay, and you see the order of members in an orthonormal basis, that can be thought of as an orientation. Okay, and if you apply to an orthonormal basis an orthogonal transformation of determinant 1, it will keep the orientation. If you apply an orthogonal transformation of determinant minus 1, it will reverse the orientation. And this keeping the orientation or reversing the orientation, how do you determine it? See, after all, what this is going to do is, for example, if you look at the R3 situation, okay, if I start with I, J, K, which are the standard bases, E1, E2, E3 in R3, we normally call them as I, J, K. Okay, now I, J, K, if you apply a 3 by 3 orthogonal matrix, it will go to 3 vectors, image of I, image of J, image of K. Now IJK is right-handed. Okay, but this image of I, image of J and image of K, if you take, it can be right-handed or it can be left-handed, and you will see that if the determinant is positive, if and only if that happens, then the images continue to be right-handed. If the determinant is negative, okay, then the image becomes left-handed. So what happens is, the determinant being positive is the condition that orientation is preserved. So the moral of the story is, if you want to look at orthogonal group elements which preserve the orientation, okay, which are precisely what are called the linear, rigid motions. The linear rigid motions are, mind you, they are going to be linear isometries. Okay, there will be no translation component. Mind you, the moment you say linear map, the translation component is 0. Any rigid motion is a linear isometry followed by a translation. Okay, if the original rigid motion itself is linear, then the translation component is 0. Okay, if the original rigid motion is already linear, you will get a linear isometry. But the point is that it is not just any linear isometry, it will be a linear isometry that preserves the orientation. Therefore, you will get determinant 1 members of the orthogonal group, and this forms a subgroup of the orthogonal group called the special orthogonal group. Okay, so let me write this. ONR is actually broken into 2 parts. SONR, this is called the special orthogonal group, and disjoint union. Okay, you will get the other part is so let me so what do I'll just put ON minus R. Okay, these are members of ON R with determinant equal to -1. Okay, and this SONR is going to be members of ONR with determinant equal to +1. Okay, and I want to just say that, you see, the symbol that I have used here, this is called disjoint union. That means this is used when you write disjoint union. It means it's union of 2 sets, and the 2 sets have nothing in common. So this part is determinant +1. This other one is called determinant -1. Okay, so okay, and please be careful. There is a there is a minus here, right? And here is a big deal. What is important for us is that this SONR, these are exactly the linear rigid motions. Okay, and what is a general rigid motion? A general rigid motion is, mind you, it can be written as a linear rigid motion followed by a translation. So that is the definition of a general rigid motion. So general rigid motion is the same as general oriented isometry. Okay, and remember that any isometry, if you call it as F, we have already done this. You can write F as translation by F0 composed with GF, okay, where GF is the associated linear isometry. So GF is just given by F minus F of 0. This is the linear isometry associated to F, okay, and this is translation by F of 0. Okay, it is a map V going to V plus F0, right? And any isometry can be broken down like this. What is an oriented isometry? Oriented isometry means that you can again break it as a translation and a linear isometry. The point is that this linear isometry, if you generally write it, this will be in the orthogonal group. But if it is an oriented isometry, then this will not go in ON, it will actually land in SON as a matrix. Okay, so the so I want to just say that that is equal to translation. So if I call this as F, this will be TF0, TF of 0, circle GF, and now this GF will be in SON, SONR. Okay, So the important thing is that any rigid motion can be written mathematically. It can be written as as first a linear transformation defined by a member of the special orthogonal group, namely orthogonal matrix with determinant 1, followed by a translation. And this orientation, we don't bother about the translation because translations will always preserve the orientation. They will not mess up the orientation. It's only the orthogonal group part which will actually mess up with the orientations. And in fact, if you do a little bit more analysis, you will see that the members of the orthogonal group can be thought of as generalized rotations. That's why it's called the rotation group. Okay, so basically the idea is that any isometry can be broken down into a rotation followed by translation, a generalized rotation followed by translation. This generalized rotation is a member of the orthogonal group, and then there's a translation. And a rigid motion is a orientation preserving isometry. And when you take an orientation preserving isometry and break it down into a translation and orthogonal group element, which is a rotation, you will not just get a rotation, you will get an orientation preserving rotation. And that's an element of the special orthogonal group. Okay, so the members of the special orthogonal group are those which preserve the orientation. And what is an example, what is a standard example of something that reverses the orientation? It is reflection. Reflection is a standard example that it will change the sense, it will change the orientation. Okay, so you can imagine that all these reflections will not be in SON, they will be in ON minus. Okay, but it is mathematically it's very intriguing that by composing reflections, okay, you can get all the members of the orthogonal group. Okay, the point is you may wonder how you can get orientation preserving things which are in SON by composing with reflections which are not in SON. The fact is, if you apply two orientation reversing things, the effect becomes orientation preserving. That's the whole point. So it is a very general theorem that a general isometry you can actually write it as a composition of n plus 1 reflections. And if the general isometry fixes even a single point, you can actually write it as a composition of n reflections. This is a deep theorem due to Cartan. Okay, so this goes into the study of isometry groups. Okay, but we will not need that. What I need you to understand is we need the correct mathematical interpretation of what a rigid motion is, and that is you can break it into a translation. First into a orientation preserving rotation, which is a member of the special orthogonal group. Okay, that means member of the orthogonal group with determinant 1, followed by a translation. So this interpretation we need. And where are we going to apply it? We are going to apply it to the following situation. Take a unit speed parameterized curve, apply a rigid motion, then the new curve that you are going to get will have the same curvature and torsion functions as the original curve. Okay, so that's what that's why we wanted to do all this. See, you are breaking it down by a first you see the one that in the composition, the one that comes on the right is the first map to be applied because your argument is on the right. Okay, and then only so when you write it like this, it is rotation followed by translation. Okay, but you can also write it as translation followed by rotation. That's another way of decomposing it. Okay, and the interesting thing will be that you decompose it both ways. What will happen is the rotation part will not change, only the translation part will change, and this will lead to the fact that conjugation of a translation by a rotation is again a translation. And this is more deeply connected with the fact that the isometry group is a semi-direct product of the orthogonal group and the group of translations. So this has got to do with group theory, and it is connected with the fact that the orthogonal group, if you take the orthogonal group and the translation group and you simply take the product group, that is not the full isometry group. Just the product group structure is not enough. You have to have a twisted product, which is called the semi-direct product. And it's only as a semi-direct product you will get the Euclidean group. of all isometries. Okay.